So hi guys. Today I'm just gonna talk about what I learned today. Um, I'm doing my like my side project and implementing B-tree from the TypeScript because I'm trying to make some kind of small database application using Electron, but I feel and to make some kind of like database tools and stuff, and I have to make indexing algorithm first. So I use the B-tree for it, and the reason and I don't want to really like copy this kind of code from the Google or some kind of website. Um, the first thing is why, but the thing is that because the reason I chose this kind of side project is for improve my CS knowledge. Um, I'm I'm third grade. I already turned third grade in this year, and I'm 22, and I feel like nowadays a lot of college and especially my college. I'm not gonna talk about my college. Is they really don't make teach us the practical thing. So, example, if it is really core computer science, and I already know that because I've been in the tech industry for the 9 months, but it was not really like small stuff. It was really big tech company. I worked there on this contract software engineer, and I came back to the school, and what I learned is they're not teaching us as a practical thing. What do you mean by that? Um, Example, this is kind of the thing, the the depth of the computer science that you imagine. And let's say the depth of the computer science can label like this. So this guy is most deepest thing. What the college do is they teach us like really slight of this part. And also they emphasize just memorizing rather than thinking it like rather than like trying to think why I have to use it, why this algorithm or this kind of techniques are being used in industry, and they're not trying to talk about this. So the problem of this is even though they go deep, so and let's say I think let's say this part, this green thing is necessary things even in the industry. In industry they really emphasize computer science knowledge, and the core thing I have to understand is kind of the green part. But the now college, especially my college, what they do is they sometimes go deep, but they go deep on this part, not the computer science that the industry wants, and they emphasize memorizing. So if I'm trying to, I'm like trying to ask or trying to make this kind of content into suitable for this kind of the green part, they won't. They're not gonna switch it. Because the problem is that they're not really software engineer. They don't have a job. They're sometimes they never have a experience of software engineering, so they just do the thing. Yeah. So I finally learned those kind of thing, and I know my grade is kind of really not good, but I'm trying to keep it this way rather than. So what I mean this way, rather than follow what they talk to me, I just rather study alone. But this part, I rather study alone this part by myself rather than following those kind of thing. Because this is really core thing, and even though I follow this kind of like the knowledge that they talk about, but I don't think it's kind of able to maintain after 10 years or after 6 months. I'm just gonna really forget everything because I just they emphasize memorizing. If the knowledge that doesn't use in some kind of practical way, you always forget it. So this is one way. So I'm making the B-tree. So algorithm. The first thing my mistake was the putting some kind of all of the business logic in the one class. This is because I already don't have like experience of making algorithm from the scratch. Also, rather than think about like flexibility, I just put all of the logic because rather than in that moment while writing this code, the priority of making this is just for understanding B-tree algorithm from the scratch, not making the code clean. So, and this is also valid from a lot of things. Example, like even the clean code. If you make something, you make some kind of this kind of shape of the code. If you're trying to abstract it, it will eventually be like this. If you're trying to abstract it, and it will become like this. So it will be stable for this part and the other part. The problem is that those kind of abstractions are sometimes over engineering. You have to think about like those kind of shape that can really handle by other code, because abstraction means that your abstraction code can be has to be kind of usability. You have to increase the usability for if you're trying to do the abstraction for your code. But the thing is that you never face the problem, and if you're trying to make some kind of like abstractions, and you really have to think about the problem that you never faced, but you guess that we're faced, and you just somehow make abstractions. And those kind of thing is making the time of the making the time cost very rapidly. So what I did I just make it, I just build it, but when I think that this code is not sustainable, maintainable, I just do the pivot and I just rewrite the code as not possible, because this code was just for the understanding. So based on those kind of things, I migrate the insertion logic and search operation logic. The problem of the origin one was putting all of the logic into one class, and it's not really good for the flexibility, because if you look at the search logic in this part, this search logic only valid for the recursion. So this search, it just is searching or the full whole tree, and there's no search in just one page. So that leads some kind of problem, and I knew that this is time to refactor, and this is how I refactor. Of course, I maintain the insert, not this one. And of course, I maintain the code. I maintain the logic of it. Example, searching tree, it's just like saying of this part, but there's the search in page. So after search in page, if I found some kind of query key in my page, and if there's more children, I search on tree more. So search in tree is just kind of like utilization of the search in page. So search in page is really pure that I can really use it in everywhere. Example, there's a new migrate operation which is called insert operation. If you look at my insertion logic, like before migration, it's not really understandable. I somehow get the parent node argument and I revise it via method, and that's really not good. But in this, if you look at here, in my new migrate insertion logic, I also split into insert in page and insert in tree. And also the before I make the search in page, right? The logic. I utilize search in page logic, and after I get it and if I found the core key, return it. If the lift node, if it's lift node or if it is able to insert, I insert in the page. Inserting the page is a kind of really not that pure, but just I have to really more refactory, but it's kind of really there's no kind of big dependency of it. But case 3, if page is gonna be overflow, if I'm trying to insert it, if page is gonna overflow, I do the propagation that split into two children and promote the primary key. And I inserted the new parent and search in. I do the search in page logic and the same thing. And so let's try to compare this kind of insert logic before the migration. And if you're trying to read this code line by line, and there's something called as the promote incoming page as a parent. Okay, if you're trying to click here, okay, there's more of it, and there's a split operation. Okay, there's split operation, nice, but there's bunch of methods from. It's like over how many lines of it? It's over 5. It's like 564 lines. So it's too much for you trying to figure out the insertion logic. But in this part, my migrate logic is quite simple. Okay, I search, there's a result, but if there already exists, just return it. But if I able to insert it. But if I try to insert it, but that caused the page overflow, I split it and I push the primary key into parent. And after that, I do recursive because my parent that already get the primary key because the chart is overflow. But this page, this promoted page could be also leads to the overflow. So I do the recursion of this part. So there's no big, there's only like really like difficult logic on just one logic because the propagation is kind of could be difficult, but it's not really that hard. And before, the common issue was if it's like root, and if you're trying to find the parent page, because if your page is full, you have to find the parent page and you have to promote the primary key, right? But if it's root, there's no parent page. And the origin one was making from the scratch via compare, putting if, but this is not really necessary. So I get rid of this, but I just transfer into this part. The parent page could be undefined, or it could be, or the page of it. If it's undefined, I create a new page and I create this as a new parent page, and I split into root page and I put it into as a children. But if there's already parent page, we don't really have to create a new page. We just have to insert and split operation on the original page and then put it into parent page. And that's what's really simple. And this is the screenshot of the test code. Let's validate this kind of bit tree. Since the bit tree, the minimum degree is 3, not 2, it really follows those kind of rule that, okay, there's an 8 and there's a left and right. Since 4 is more than 8, and it has to be going to left, and 12 is bigger than the 8, it has to be right of the 8. And 2 is smaller than 4, it has to go into left, and 6 is bigger than the 4, it has to go to the right. And we do same thing. Yeah, but what if I put the the bunch of the node here, like minus like 0 and minus 1 and minus 2. Since we already can get the primary index, which is t minus 1, currently our t is 2, so our index, the primary index is 1. So we can just delete this and put into primary index here. And now we can just make it as like this. It's really simple. The bit tree is really simple if you're trying to understand it. If you're trying to like understand the core factor of it. The 36, 34, 38, 37, 39. So this is already valid, and the test case was really nice. And even the utils, I put some kind of formula on the utils part, because this kind of tree thing here, the max number of the key formula and the mean number of key formulas, those kind of thing is never gonna be changed, because that is the like really already for math formula of the bit tree. So I just put into utils because that has to be that's gonna be changed. That's not gonna be changed. So even the page logic, so if it's like really gonna be used a lot, I put in the page. So the reason why I didn't use the left right, like the pointers variable, I don't really have to do it. And the reason why this kind of code is like big for you, this code could be kind of weird, but I think this is the core principle of my code, the insertion on search or deletion logic. Example, you have, let's say like this. So 32 is gonna be root, right? It's 32. So that's gonna be, the key is 30. Wait, this is too big. The key is 32, right? Wait, hold on. Never mind. So key is 32, and the children has to be 48. So 48 here. What else? 16, 48. Wait. I think there's one, but never mind. So there's a 16 and 48. So I will give you some kind of problems that your core key is, let's say, 50. Your children is 16 and 48. The 50, there's no 50 in this kind of your children, right? But if you look, and basically you just have to go with the child index 1. But how that's really possible? Because we just use this kind of logic here. We find index that query is smaller than the element. Since 50 is not smaller than 32, and this index is gonna be -1, because there's no element that matches with this kind of statement. So that's -1, but that means that it already overflows of the 32. So that has to be going to the right of it. Since the 50 is already bigger than the 32, we just have to return the list, the array length. So this array length is actually 1, and we can just go to the children that is 1, which is 48, rather than 16. So we don't really have to think about those kind of left, right pointer, those kind of thing. And that also valid in this logic. So this is it. Have a nice day. See you next time. Bye bye.